Good day, everyone, and welcome to the CelPlan Webinar Series 2014. This is the 5th webinar of our series. Today's webinar is what LTE parameters need to be dimensioned and optimized. It's part 2 of the webinar that was originally presented. Part 1 was presented on September 3rd. The presenter today is Mr. Leonard Korowajczyk, and he will give a more detailed introduction of himself once I turn the floor over to him. Just a few logistics to go over. If you have any questions, you will see in your panel that there is a hand that you can actually raise to ask a question. We will try to entertain the questions as they come in, or actually we will take a break in between the presentation to answer questions. We may not be able to get to all the questions during the presentation, and those that we're not able to get to, we will at least answer via email, so do send in your questions. If there are any other issues, etc., please, there's a chat window there to which you can ping to us and let us know if you're experiencing any issues, and we will try to address them in as shortest period of time as possible. Without further ado, I would like to turn the session over to Leonard.
Good morning, good afternoon, good evening. We have a audience from around the world. It's a pleasure to be here again and to give this part 2 of the webinar, what LTE parameters need to be dimensioned and optimized. Let's go to the introduction. My name is Leonard Korowajczyk. I am the CEO and CTO of CelPlan International and have been around for quite a while. 45 years of experience in the telecom field, mainly in R&D, manufacturing and service areas. Have several patents, and we as a company have published 2 books already through Wiley, Designing CDMA 2000 System. This book has half of it dedicated to the design of wireless networks in general, not just CDMA, and the LTE by Max and WLAN book published in 2011, and we are now writing the 2nd edition of this book. So a lot of the material from this webinar comes from the will be in the 2nd edition. All this effort, of course, is effort of the team, of CelPlan team, that has been very diligently analyzing and developing the specifications for our tools and also designing many networks around the world. We are writing several other books that should be published very shortly. Now let's talk a little bit about the company, CelPlan International. We are an employee-owned company. We have headquarters in the USA, 450 plus employees. Actually, it's more than 500 employees at this moment, 550 actually. And we are 20 years in business. We have subsidiaries in 6 countries, and we operate worldwide. We are totally vendor independent. We provide network design software, design services, optimization, performance evaluation, high-level consulting, and so on. And we support all the different technologies, including some hard-to-crack issues we are generally called to help people with it. This is a very successful webinar series. We already had 4.5 webinars, so today we are finishing the 5th webinar, September 17. And we have still 2 webinars this year, spectrum analysis and MIMO. So if you have suggestions, please feel free to send them to us. Our first webinar was how to dimension user traffic in 4G networks. We had participants from 44 countries, and the YouTube views are already in 821, so it has been a very, very successful and looked webinar. Those are the topics that basically we covered in this webinar. Some are very, very unique, So that's, I think, is one of the main reasons of this success. The second webinar was how to consider overhead in LTE dimensioning and what is the impact. 49 countries, 430 views, a very solid webinar, giving also very unique views of overhead in LTE that is really very, very important to be considered to dimension any network. Those are the main topics that we discussed in this webinar. Webinar 3 was in July, how to consider customer experience when designing a wireless networks, 40 countries, 315 views. And basically, we also covered very, very important topics like SNIR, how to calculate, and how the customer experience, which parameters do affect customer experience. Webinar 4 covered LTE measurements, what they mean and how they are used, 44 countries, 373 views. And then those are the topics of the webinar. We had the network measurements part, the field measurements part, and we went very in depth in these different measurements that are done in LTE. Today's webinar, the first part, happened in September 3rd. All those webinars are available in our website and in YouTube. We had 69 countries and 574 visits in the last 15 days. Views in YouTube, so it was really something very, very popular. Today we will give, so the first part was the downlink, and today we will concentrate on the uplink. So that's what we are doing today. Just to talk a little bit about next events. The next webinar will be on October 1st, spectral analysis for LTE systems. Registration is open. So register soon because the number of participants is limited, and we don't like to leave people out, but we have a constraint in the number of participants. The spectral analysis for LTE systems we will cover many, many issues that are very, very interesting, and I think you will like. Here's the topics. You can see those topics also on our website. And the last webinar will be MIMO, what is real, what is wishful thinking. That will be on November 5th. Registration is also open. And we will have a LTE Technology Network and Design and Optimization Bootcamp in December 8 to 12. That's a full-day, full-time webinar at the University of West Indies in St. Augustine, Trinidad. And here is the program. We'll speak about the technology and the LTE network design, and there is a 4G certification optional. This is not a free class, so you should also register if you intend to participate. So let's go to today's feature presentation. What LTE parameters need to be dimensioned and optimized? Part 2, uplink. This is the total content of this webinar. So we had an LTE refresher last time, network planning, and we covered the downlink. So today we will cover the uplink, the random access, control and data. Then we will speak about resource optimization, and finally a summary. Okay. So starting the webinar, we will talk about uplink dimensioning. Random access, it will have two parts, one part about random access, another part about control and data. Let's speak about random access in LTE. Well, any packet network, it has a random access procedure. Suppose in Ethernet we use carrier sense multiple access with collision detection. In Wi-Fi we use carrier sense multiple access with collision avoidance. In 3GPP a different method was used. Of course, is not a carrier sense, but it is a kind of request and collision detection indirectly. So basically 3GPP specified this random access procedure that you will see that is very, very complex. And the reason for it is that contrary to Ethernet and Wi-Fi, that the access occupies the whole channel, in LTE it occupies a small part of the wireless uplink channel. And one of the reasons of the complexity is that it takes a while. It requires exchange of messages and so on to find out if there was a collision or not. It is a contention process though, and basically LTE dedicates a portion of the uplink frame for the contention to happen. This portion is called Physical Random Access Channel, or PRACH. Well, when does our UE need to do the LTE random access procedure? Well, when it has to access the ENB for the first time, or when when it's transitioning from RRC idle mode to RRC connected mode. And with this, it gathers from DNB the timing advance to be used by the UE. Otherwise, the UE cannot really talk to the ENB if it doesn't know exactly the timing advance to be used. It also has to do the random access when it needs uplink resource allocation, or it needs to complete an inter-system handover. To do the random access, the UE has to read some parameters that are broadcasted by the ENB in SIB1 and in SIB2. So the UE cannot even try to, or it will not be able to access the do the random access procedure without reading SIB1 and SIB2. And there are many parameters that have to be dimensioned by the network designer. You will see that it's something that is relatively complex to understand, but it's not so complex really to design the parameters. Well, let's talk about SIB1. SIB1 has many parameters, but for random access parameters, basically what needs to be done is what is the mapping of the other SIBs. So by reading SIB1, the UE will know where to find SIB2. And there is no real parameters there beside telling where to find SIB2. When this is done, then the UE can read SIB2. SIB2 has many parameters. Its periodicity is scheduled in SIB1 and can be from 8 to 512 frames. So this is also user defined. And I divided the parameters. SIB2 has many parameters. I divided them in 3 groups. The PDSCH configuration, the RACH configuration, and the PRACH configuration. So as you can see, there are many parameters, and we will cover each one of them as we go along. But it's very important to understand where those parameters come from, what is the range, and so on. Well, first we need to analyze how the random access area was designed. This area will be accessed by all the UEs connected to the UNB, so it's a shared area. And of course, one UE is unaware of the other UEs, so there will maybe conflicts. To minimize the number of conflicts, because several UEs will access PRACH at the same time, the 3GPP designed this area providing 64 orthogonal codes for simultaneous access. So theoretically, up to 64 UEs could access this area at the same time. One thing that is very important is that these codes, they do not carry any information. Basically, besides saying, look, this UE is requesting access, has an UE, because the UE is not identified. An UE is requesting access, has chosen one of the 64 codes, and is requesting its timing advance information. And of course, the PRACH area removes capacity from the uplink access, so it's taking part of the uplink frame. 3GPP reserved 6 physical resource blocks by 1 to 2 subframes for the random access. Again, those 1 to 3 subframes are dimensioned by the network designer, but it's a small portion of the uplink frame. Although the number of random accesses can be, there may be many random access areas even in one frame. So again, all of this has to be dimensioned by the user. One thing that it's very, very, very important to stress and to understand is that the uplink frame is formed at the ENB antenna. So it's after the signal propagates from the UE, it should arrive at the ENB antenna at a certain moment. But for the random access, the UE is not yet synchronized, doesn't use yet a timing advance, doesn't know how far it is from the ENB, so there must be a flexibility to accommodate the traveling time from the UE to the random access area. So in principle, the UE assumes that it is close to the ENB and doesn't do any timing advance. So it transmits when it receives the downlink frame. So it assumes that it is collocated with the ENB antenna. But the transmissions of the UE, they will arrive delayed in time, proportionally to the distance. What we need to consider is that there is a round trip time. So there is every 300 meters, because the light propagates 300 meters in 1 microsecond, but because the signal has to come from the ENB to the UE and then go from the UE to the ENB, every 300 meters we need to consider 2 microseconds. The orthogonal codes selected by 3GPP are the Zadoff-Chu codes that we already covered in the first part. And those codes, they can provide several sequences, and those sequences are not totally orthogonal between themselves. Some are more, some are less orthogonal. But the important property is that one specific ZC sequence, it is orthogonal to its own shifts. So when the sequence is shifted, the shifts are orthogonal. And this allows to detect multipaths and so on. So in the designing the random access area, the 3GPP considered a cyclic prefix, and this cyclic prefix has to be large because it has to accommodate the round trip between the ENB and the UE. It considered a preamble that carries the Zadoff-Chu code and a guard time that avoids interference outside the subframe. So remember that it has 1 to 3 subframes, but it needs to have inside a guard time. And also the basic PRACH was designed for a cell range of 15 kilometers. And this leads to a CP and a GT of approximately 100 microseconds. So if we take one subframe, it's 1 millisecond. We discount 200 microseconds. We have left for the preamble 800 microseconds. Well, if you go to the basics of digital communications, you will see that 800 microseconds symbol corresponds a bandwidth of 1.25 kilohertz. One is the inverse of the other. So in principle, to get only one symbol, a preamble, only one symbol, we need to change our OFDM step in terms of subcarriers, and instead of using 15 kilohertz spacing between subcarriers, we will use 1.25 kilohertz spacing between subcarriers. So here we show on the left side a whole uplink frame with the subframes of 1 millisecond. The frame has 10 milliseconds. And in blue, we depict then the random access area. It has a cyclic prefix in the beginning, the preamble, and a guard time in the end. The preamble is not, subcarriers are not spaced with 15 kilohertz as the remaining, but they are spaced at 1.25 kilohertz. So with this, we have 839 subcarriers here. And one symbol with a duration of 800 microseconds, one symbol per subcarrier. And those 839 subcarriers carry then 838 long Zadoff-Chu code. Okay, well, 3GPP doesn't make things simple, so they specified 5 formats for the PRACH area. And this is denominated PRACH configuration indexes. Okay, here are the formats 0, 1, 2, 3, 4. Just to remind you, there are a number of root sequences that are 838. For TDD, there is a special format, for format 4, that has only 138 sequences, because for TDD, the PRACH area can be sent on the TDD special frames that are shorter. So basically the 0, 1, 2, and 3 formats, They are FDD and TDD. And here are the main information. Well, why do we have so many formats? Basically, the reason to have those formats is the size of the cell. So for a medium cell, the maximum cell range for format 0 is 14.5 kilometers. For very, very large cells, we can use format 1 that has a cell range of 77.3 kilometers. And both have 800 microseconds preamble, and they use one PRACH symbol or also one or two subframes. The need for a second subframe here is because the guard times are very large due to the very large cell size. And the other format is also for large cells and extra large cells that can go to 107 kilometers and so on, and they use two symbols. And the reason to use two symbols is so it's possible to gather more energy. The symbols you send the same code, and so we get a 3 dB gain, and it's up to the designer to choose which one of those formats. Most probably the bulk of the designs will use Preamble format 0. Here we have a depiction on the right hand side of the Preamble format 0, where we have on the sides we have one subcarrier guard band, and then we have the CP, the Preamble, and the GT. Here I made a depiction of the four formats, not the TDD one, but the other ones. And basically what I'm showing here are the width of the random access area, that is 1.080 megahertz. We have the 15 kilohertz guard band on each side, and then we have the 839 subcarriers. For TDD is this drawing here. It occupies only 0.16 of a subframe, and of course it has, the width is the same, it just has a shorter preamble. And here I show the configuration: format 0, format 1 with one preamble but very large CP and GT, format 2 with now two preambles and smaller CPs and GTs, and format 3 where we have two preambles and very large. And of course all of these will eat uplink real estate. One thing that I need to stress is how the preamble detection is done. This is very, very important if you want to understand how you have to dimension random access parameters going forward. In regular OFDM, to detect the regular channels and so on, we need to be very well synchronized to the starting of the subframe. And the reason for this is that we have to detect sines and cosines, and if we are not synchronized, the sign is not a sign anymore, and it's something else. It's a sign with a phase shift, so it cannot be properly extracted. Here we have something similar, because as we already discussed, the preambles will arrive at different moments. So let's show here the start of the subframe boundary. So this is subframe boundary, and of course if we have UE that is collocated with the ENB or very, very, very close, it will arrive at the right moment. But we have an UE that can be far away, and it will arrive after round trip time plus delay spread. So it will arrive in this moment, and we have then several UEs in the middle. What will happen is that the detection of the Zadoff-Chu code will be not exactly what it is, but it will be a shifted Zadoff-Chu code. And this shift will give us a wrong impression, so it has to be considered what is the maximum shift. So Zadoff-Chu codes that when allocated, they cannot be, they have to consider this distance or this phase shift to be allocated. So this is very, very important. And basically, we will see that we will consider all of this in the dimensioning of the random access parameters. On the guard time, we can see here that the guard time invades the next symbol, the next subframe. But of course, because the next subframe has a CP and the guard time is empty, there is no real harm in invading it. But the maximum invasion is of the size of the CP. And all of this is calculated when we are going to dimension the parameters. So let's summarize what is the random access area according to the 3GPP design. Well, we already spoke about Zadoff-Chu code. ZC code is orthogonal to its shifted copies. Different ZC codes are not fully orthogonal. And the travel time adds to the original shift of the ZC code. So basically, if we want orthogonal codes, we apply shifts to the ZC code. But these shifts will have an additional shift due to the travel time to and from the UE. Neighbor cells should use different orthogonal codes to avoid inter-cell interference. And that's something that we will plan and we will show how it should be done. 3GPP assumed that a cell should have 64 codes available for random access. Well, we know that there are 838 possible codes, orthogonal codes, or nearly orthogonal codes, but a cell needs only to have 64 codes. And those codes can be different sequences or different shifts in the of the same sequence. And at the same time, they did the design to support up to 120 kilometers and assume that a reuse of 12 should be sufficient to avoid interference. Well, the 120 kilometers leads to a symbol of 800 microseconds, so it basically consubstantiates what we already said, and consequently a carrier spacing of 1.25 kilometers. Well, with this we need 64 with a reuse of 12, so we need 768 subcarriers. And what 3GPP did, it basically rounded to 6 regular resource blocks, and with this, and those resource blocks could accommodate 864 subcarriers with a spacing of 1.25. But as we need the guard bands, in the end we got 838 Zadoff-Chu code shifts, or 839 subcarriers. And of course, we add a cyclic prefix and a guard time to the beginning and to the end, as we already said. And it allowed the use of 1, 2, or 3 subframes. So we have appropriate margins of guard times to accommodate the 120 kilometers maximum. Okay, once we understand how the random access area was designed and what criteria was used, let's look at the random access procedure. Well, DOE, as I already said, has to first read CB2. And in CB2, it will read several parameters. One of the parameters that it will read is the target receive power level. It means that what is the level that should arrive at the ENB from the UE. Well, the UE doesn't know how far it is. So the only way to place this level inside the target, and the target can be between -120 to -90. So it's up to this network designer to specify the value. Let's suppose that we specified -100. So because UE doesn't know where it is, it will do a calculation, and it will start with a very low power, and then ramp up this power in steps that also are dimensioned by the designers, and those steps can be 0 to 4 or 6 dBs. Of course, each time that the UE tries to access, it has to wait for a reply that will come 4 subframes later, and so on and so on. So you don't want to have many trials, but also you don't want to saturate the ENB receiver. That will be disastrous. So basically we can do several tries, and the maximum number of tries is also specified in this very large range. So the designer has to choose one of those values. And the UE basically sends the signal and waits for a response. This response will come within a specified window, again by the designer, that can be 2, 3, 4, 5, 6, 7, 8, or 10 subframes later. Of course, larger the window, longer the random access process will take. Okay, this is a very crowded slide, and I'm quite sure you are not able to read what is here on the right-hand side. But you're not supposed to read this. I just want to show you here the extent of the random access procedure, and I divide it in 3 blocks. The UE performs a random access. Basically how it does, it sends a signal, the signal doesn't reach, it increases by a step, it still doesn't reach, it increases by another step, nothing, another step, nothing, until it does reach the ENB with the desired target level. What happens then is that the ENB replies through the PDCCA channel with what we call here the random access response. So this is the second part of the access procedure. And finally, just receiving the response is not enough, because as I said, the UE did not identify itself. What the UE did was to choose one of the 64 codes, and it is identified by this code. But two UEs may have chosen the same code, and the two UEs may think that the RAR response, the RAR message is for them. So there is a conflict. So there is another procedure that is the contention resolution to see. So if there was a contention, everything has to start from scratch again. Okay, the only difference now is that the UE does not have to increase the PRACH access so many times, because it already knows, well, actually it doesn't know, because it knows that there was a conflict, but it knows with which level it reached the ENB. So what we are showing here is this first part. The UE performs a random access, and I hope you can read the flux here, the diagram flow. So again, what will be done now is that the UE reads the SIP2, some of the SIP2 parameters, and in this case it will read the PRACH configuration index. And this is a number from 0 to 63. By reading the configuration index, it can figure out what is the preamble format that is defined by the cell range, what is the preamble density that is defined by the amount of traffic that is expected, and what is the preamble version, or where the preamble is placed in the subframes. And there are 16 configurations per format, and 1 to 5 subframes per frame can carry the PRACH area. Another parameter that is also signaled is the PRACH frequency offset, because it's not enough to know that you are inside a subframe. You need to know where in the subframe you are. A good design will always place the PRACH area adjacent to the PUCCH channels. So there is, to avoid a break for the PUSCH channels. The next information that is sent in the SIP2. So with these two first informations, the UE figures out where it should send the preamble, the random access, where it should be done. Then it has to know what we call the zero correlation zone. So it has to figure out how many route sequences will be required, and this is based on the size of the cell, and consequently on the shifts that have to be done to get orthogonal codes. And one shift corresponds a cell range of 143 meters. So if our cell range is 1.43 kilometers, we need to give 10 shifts. Also, the zero correlation zone is modified by the Doppler effect for high speed. So there is a high speed flag that indicates when the UE is moving above 200 kilometers per hour, and this indicates if there will be an additional shift due to Doppler effect. Well, another parameter that needs to be chosen is the root sequence index. So which of the 838 sequences will be used for the access to this cell. So all of this the UE gathers from SIP2. Besides, not all the 64 orthogonal messages are available because the cell or the designer of the cell can divide those messages in 3 groups. Group A, Group B, that are contention groups, and 1 non-contention group. And here are the limits for each group. The reason for this is to allow the UE to send an implicit message when it chooses one of the groups. So as I told, the Zadoff-Chu code doesn't carry any information. So one way to convey some kind of information was to allowing the UE to choose between 2 groups, Group A and Group B. And Group A means that, look, I have a small message to send, or I am in a very poor coverage area. I cannot send large messages at once, so I need a small allocation. Group B means that I have large message to send and I am in a good coverage. So this is a way of sending implicitly a message by selecting the codes. But by dividing in 2 groups, you may run out of codes in one of them, and that creates some kind of constraint. Besides, once the UE is already established a connection with the ENB and so on, the ENB can ask the UE to do access through the codes that are in the non-contention group. So those codes are assigned by the ENB to specific UEs, so there will be no contention. Consequently, the communication is more efficient. Although it is possible to the designer can decide to not have the non-contention group. It needs to always to have Group A and Group B. Okay. So let's go and quickly through the flow. Basically, the UE starts reading SIP1 and SIP2, and it has access to the ENB. Why? Because it wants to access the ENB and move from RRC idle to RRC connected, and also it needs to request uplink resources, or it needs to do inter-system handover. So for any one of these reasons, it will perform the access. Basically, what do you then do? It reads the PRACH configuration index and the PRACH frequency offset to access the frame that carries the PRACH. It selects the root sequence index, a random preamble sequence. So it selects one of the 64, or depending on how it's organized in Group A and Group B, and it sends the message. This sequence is identified by what we call RAPID, Random Access Preamble Identification. Remember that I told you that it will start with low power. So it starts, waits for a reply. It checks if the maximum number of preamble transmission was reached. If it was reached, it will start everything from scratch again. If it didn't reach, it will increment the number of preamble transmissions. And at this moment, it will then adjust the initial power and increase by a step. And it will transmit considering zero time advance. So at this moment, the UE is accessing the random access area. Okay, let's speak a little bit about the physical random access channel, PRACH. We'll speak about the RAC, random access channel, the PRACH formats, configuration index, frequency offset, zero correlation zone, high-speed flag, and root sequence index. We already discussed all of this, so basically we'll go a little bit deeper now. Random access channel. So basically, this is the channel that used to transfer random access preamble control between MAC and PHY. RAC does not transfer any higher layer messages, so there is no real messages beside the implicit messages or implicit information that I already told you about. So PHY is responsible to calculate the PRACH transmit power, to select the preamble sequence, and to transmit the PRACH. Well, there are some SIP2 parameters that are used during power calculation, and those are power ramping step, preamble initial receive target power, and preamble maximum transmissions. The preamble transmit power is calculated using this formula that is based on the maximum UE transmit, the minimum of the maximum transmit power or the path loss plus a preamble RX target power. So of course, if it reaches the UE limit, it will stop there. The preamble receive target power is based on preamble initial receive target power plus a delta preamble plus the counter times the power ramping step, because you may be already in the third, fourth try. And the delta preamble is predefined by 3GPP for 0 and minus 3 dB for the different formats. The idea here is that all the accesses, they come with a very similar power, they arrive with very similar power, maximum power at the ENB. That is the receive target power. So they should come very, very close within this margin so they can be detected. Well, we need to define the preamble format, and this comes on SIP2. We need to define the root sequence index. And the root sequence index is calculated by analyzing those parameters sent in SIP. And the PRACH configuration index basically is a sequence that goes from 1 to 836 or 1 to 138, depending on the format chosen. The zero correlation zone value defines the number of sequences required by each cell, because depending on the size of the cell, we can only do so many shifts that are really orthogonal, because the shields have to be spaced. by a certain amount depending on the number of cell or the size of the cell. So then one sequence is not enough. We need to take a second, a third, a fourth sequence. And basically, for some very special cases, we need to take into account tables that take the Doppler effect. The way it is done is that the planning tool allocates the sequences using a logical sequence numbering. So it means 1, 2, 3, 4, a sequential sequence. But because not all sequences are orthogonal, or some are more orthogonal than the others, what the GPP does, it gives us a table that maps, the table will come later, that maps the logical numbering to another numbering that tries to place orthogonal codes together, more orthogonal codes, sequences together. So just basically go to the channel format, the PRACH format. We already discussed about this. So basically format is connected to the size of the cell and is something that is defined for the cell. So a cell will use one of those preamble formats, and that's why it's very important to understand what the format means, how it was designed, so the designer can choose one of those formats that best is a best fit for it. And I have here the same thing now with the design, with the drawing of the two formats. When we go to the PRACH configuration index, basically we already discussed this also. We need to specify for each cell 64 codes that the UE can choose. Okay, and those codes are divided, as we already said, in contention group A, contention group B, and non-contention group. And here are is the formula that defines when a message should be in group A or in group B. Here now we have the complete set of SIB information, SIB2 information parameters related to the random access. In the RACH configuration, we have a number of random access parameters, 4 to 64. Size of array preamble group A, 4 to 60. Message size of group A. So when it says step, it means that you cannot choose 5. It should be 4, 8, 12, and so on. Message size group A. Message power of set group B. So for the designer should specify, suppose 144. Okay, so if the message has 144 bits, it will be group A. Or it can specify 256 bits, but it has only 4 values to choose. And in group B, it will specify what is the power of set for it. Then it will specify the power ramping step that can be 2, 4, 6, or even 0. It specifies the receive target power, maximum number of transmissions, when the response should be expected, how many frames later, and then the Mach contention resolution and the number of arc retransmissions. On the PDSCH, the reference signal power is important, the power boost, we explained this already on the downlink. And then it will specify the root sequence index. So all of this has to be calculated by the designer for each cell. What is the PRACH configuration index? Is the high-speed flag true or false? What is the zero correlation zone configuration? And the PRACH frequency offset. Okay, the PRACH configuration index then, it mixes the preamble format, the subframe number, the frame number, the subframe number, and the rack density per frame. So for preamble format 0, it has 16 indexes, and those indexes then say if it is used in all frames or only in even frames. So this one is in all frames, and it is available on frame number 1, so the density is 1 PRACH per frame. Here it was half, and here it will be 2, 3, 4, 5, up to 10. So basically the configuration index specifies for each format what is the preamble and what is the density and where in which subframe it is located. So it says here that is located in those subframes. So this will allow the UE to know where it should send the PRACH information. What is missing here is that, okay, it knows the subframe, it will choose one of the subframes. Now it doesn't know inside the subframe where exactly is the PRACH area. And for this it needs the PRACH frequency offset. So here the offset is 2. So it means that 2 resource blocks later starts the cyclic prefix. It can be 4, it can be 6, it can be 8. Okay, so by knowing the subframe and knowing the frequency offset, it can, and the format, it can locate the area. The next parameter that we need to know, what is the PRACH correlation zone? And this correlation zone is informed by an index. So it's a number from 0 to 16. And basically what it means is that this number is related to a cell range. So if we have a very small cell, 760 meters, we can use only one root sequence. This root sequence will allow us to have 64 orthogonal codes because I only need a cyclic shift of 13 due to this distance. But if I have now a large cell of 5.48 kilometers, I need to use now 4 sequences, and I will have 18 orthogonal codes per sequence with a cyclic shift of 46, and so on and so on and so on until I reach close to 120 kilometers, where I need to use now 64 sequences with a shift of 1. Sorry, with a shift of 838, so I will have only one root sequence. And then this 3GPP has other tables that considers the high-speed flag. So in this case, it has an index that goes to 6, 0 to 6, when the flag is true, but it's also based on cell range in kilometers. The PRACH high-speed flag is basically one value. It's only considered when the UE is moving beyond 250 kilometers per hour. And then we have the PRACH route sequence index that has to be allocated. And remember what we said is that we take those sequences and we allocate them in a sequential way, trying to space the same numbers as much as possible, trying to put the sequence indices as far as possible away. What the 3GPP does, it prepares this table here that maps logical sequence numbers to actual sequences. So what happens now is that because those numbers will be close to each other, it chooses sequences that are orthogonal to, as much orthogonal as possible to each other. So that's why it does this mapping. So when we design, we will design like this. So in this cell we will put 0, 1, 2, and 3. But in reality, after we use the table, the sequences adopted and that will be informed is 129, 710, 140, and 699. So you can see that there is a mapping because 0, 1, and 2, and 3 sequences, they are not very orthogonal to each other. But those ones are nearly completely orthogonal and so on. So all this mapping has to be done, and of course you need a tool to do this because doing by hand it's very prone to errors and very cumbersome. So in this case, what we did here, we consider a range of 5 kilometers, so which requires a format 0, a 0 correlation zone of 8, 4 root sequences per cell, resulting in a reuse pattern of 209. So basically the tool then does the logical allocation, and what we do then is the mapping of this allocation to the actual sequence numbers. Well, we finished part 1 of the random access procedure. We are going now to part 2. In part 2, is this part here is where the UE looks for random access response. And here we have then a better view of the flow. So UE already transmitted the PRACH, considering 0 time advance and using the calculated power and so on. So now the UE starts looking within the window specified in CIV2 for a PDCCH that is scrambled with the RI-RNTI, and this RI-RNTI is a single value for all UEs. So it's trying to find, is there a response for a random access mapped in, to the PRACH opportunity in which it was transmitted. So basically what will happen now, it looks in the window. If it doesn't find, it goes back inside the window, and that can be 2, 3, 4, 8 frames, 2 frames. It will go back and increase the power again. So if it didn't detect the message, it boosts the power and retransmit again. If it did detect the message, it decodes the RAR message that is in the PDSCH. It decodes RAR and looks for its rapid in all RAR listed instances. So the random access response has many rapids. And remember, rapid is the code that was chosen by the random access preamble ID that was chosen by the UE. It checks if its code is there. If its code is not there, then this message is not for it. It continues looking inside the window until it finds. If it doesn't find, it starts everything again. So rapid detected? No. Boost power, start more retransmission? Yes. Okay, if it's yes, it will go to the next stage. But let's understand the RAR message. The RAR message has two subheaders, okay, and many rapid access response payloads, okay. So the first subheader basically gives the back-off indicator, and then it will have, this is only one, and then it will have several subheaders with rapid identity, and for each one of them it will have a random response. The random response will carry the timing advance, the uplink grant, and a temporary CRNTI number. The reason that it's temporary is that it's not clear yet if there was contention or not. So maybe two UEs choose the same access code, everything, and they will get the same identification. So they will have to go to the next stage, that is the contention resolution. And this is this last stage here. So how does it perform contention resolution? Well, did it detect rapid? No. Power boost, go back. Yes. Okay. So it got now from the RAR message a back-off indicator, a timing advance, an uplink grant, and a temporary CRNTI. So at this moment, because it has the timing advance, it will transmit a layer 3 message. In the location assigned in the uplink grant. So the uplink grant gave an allocation in the uplink frame for the UE to send the data. So UE sends the message using CRNTI or the temporary CRNTI if it doesn't have the CRNTI assigned yet. And it sends the message in the place where the DCCH told it to send. And then it starts a timer. So basically, it waits for a reply to its message. If the timer expired, starts everything from scratch. If the timer doesn't expire and it detects a message, it checks if the message has the same information it sent to the ENB. Basically what the ENB does, it copy and pastes the information back. And this information contains the data, the UE data. So what the UE will do then, oh, this is not my message, so there was a conflict. This is somebody else's message, or this is garbage. So it will not say that's no. It continues until the timer expires, and then it starts again. But if it detects, it says, okay, there was no conflict, I am on, I am okay, I have my timing advance, and I can now proceed working normally. I change my RRC status. And this is basically the MAC control element that is sent to verify if there was contention or not. It's a 48 plus 8 bit, and it has an LCID That is the idea of the MAC message being sent. With this, we cover the random access. I will open here if there is any questions.
Leonard, we have a number of questions. We're running a bit behind time, so I will probably just field one from the many, and we'll get to the others via email or at the end of this sequence. Question here, how frequently does an UE have to update the timing advance?
Well, it depends on how fast it is moving. And of course, the UE doesn't know how fast it is moving. So this is something that has to be specified also in one of the timers that is sent in one of the SIPs. So basically, the UE will have to adjust according to this timer, or when it moves from one cell to the other, or when it goes to a disconnected state, and then when it comes back, it has again to adjust the timing advance. I apologize really that it's taking so long, but you can see that it's a very complex topic. People have difficulties in understanding it, although after you understand it becomes very simple. There is not really much, it's all based on cell ranges and so on. So it's very easy to do the planning, but it's essential that you understand very well what is happening and why it is being done so you can do the planning. Otherwise, you will never be able to do the planning. And you need to have the proper tool to plan for you and allocate the proper reuses and so on. Okay, so we will speak now about uplink control and data channels that are also a little bit, I wouldn't say confusing, but they are more difficult to understand than the downlink. And there are several reasons for it, because the UE doesn't have full control, so it has to do things really, a lot of things are done based on decisions that are commanded by the ENB. Well, to do anything in the uplink, the UE has to read SIP2, uplink configuration parameters. And those are the configuration parameters that are essential to processing the uplink connectivity. And they are related to the PUSCH, PUCCH, and the sounding reference signal that we will talk about. So let's start with the demodulation reference signals. Remember that in the downlink we have the cell reference signals, and those cell reference signals are used to equalize the channel. Well, in the uplink, each UE will need to have its own reference signal, because each UE is in a different place, and the ENB has to synchronize to each ENB, each UE to be able to decode it. So basically what happens here is that the demodulation reference signals are used for what? For channel estimation and synchronization. And we have then DMRS in the control channel and the uplink share channel. And we also will have another kind of reference signal that is called sounding reference signals. Well, DMRSs also use Zadoff-Chu base sequences, and there are 30 groups of those base Zadoff-Chu base sequences. And remember again, the Zadoff-Chu base sequences, they are not fully orthogonal to each other, but within a base sequence there are orthogonal to shifts of the sequence. because the uplink transmission have a variable number of resource blocks, those base sequences have to be designed with different sizes, you know, from one resource block to 100 resource blocks. So basically each group has a set of those sequences with different sizes, and each time we select the size according to the number of resource blocks being sent. So here we depict a resource, uplink base group sequence. So this is one group. We have 30 groups here, okay, and this group has a lot of sequences up to sequence, I believe it's, just one second, up to 5 resource blocks. We have only one sequence. Above 5 resource blocks, we have 2 sequences per number of resource blocks up to 100. So you can see that there is a lot of sequences that can be used. And the way we do this is that we design those sequences according to the PCI. So those sequences, those groups, they are allocated using PCI mod 30. So we avoid to allocate the same sequence close to each other. So here is a zoom, as you can see, until 5 resource blocks. So each sequence has 12 Zadoff-Chu shifts. Then the next one is larger, 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 and then from the 6 onward we have 2 sequences per number of resource blocks. Well, let's start with the physical uplink control channel. The physical uplink control channels, they are sent on the sides of the uplink frame. Basically, one channel is one resource block on one slot and one resource block on the other slot on the 2 extremes of a frame, subframe. So, and the next channel is reversed, and so on and so on. So we can have multiple channels, and you will see that those channels, they will be shared. We can allocate from 2 to 8 resource blocks for PUCCH. So this is something that again has to be dimensioned by the network designer, and it's basically dependent on traffic. Well, we have 3GPP defines several formats for the uplink channel. They like to define many formats, and all of this, of course, adds a little complexity to understand it and to make it to decide what to do and how to use it and so on. Basically, we need to divide these formats according to, I would say, the application. So the formats 1, there are 3 formats, 1A and 1B. They are basically used to send ACNAC to the messages received from the downlink and to request allocation of uplink allocation to send data. The formats 2A to B, 2A and 2B, they are used to send measurements. CSI, status channel information, channel status information, and so on. ACNAC may be added to it just to make it work. And IUE can have 2 ACNACs maximum per subframe. Format 3 was created on release, I believe, release 11, when several concatenation of several carriers, aggregation of several carriers is used. So now we need to send much more ACKs than before, because you can aggregate up to 5 carriers, 2 ACKs per carrier. So that is 10 ACKs that you can do. And then there is a possibility of bundling, so you can do theoretically up to 20 ARC. That's why we have those different formats. And also why we have 1A and 1B, 2A and 2B, again, is basically to allow us to send a little bit more information. And this information, what happens is that those signals, those channels, they are shared by different UEs. So different UEs use the same channel to send their information using orthogonal codes, and there is a lot of interference because it will be the neighbor cells will interfere and so on and so on. So there is a very large spreading factor. Format 1 has a spreading factor of 96, 1A 96 also, while 1B has a spreading factor of 48. Now when we go to format 2, you can see that the spreading factors are much smaller, and format 3 even smaller, again because there is much more information being sent. Question is, well, are the first one exaggerated or the others are underestimated, and so on? Well, the ACNAC is essential to the working of the network, so people didn't want to compromise, while the others, they are important, but not so essential. And those formats are defined here on the top for the normal and the extended cyclic prefix. So the channels are here on the side, here is the PRACH area, and the channels are here on the side. And then in the middle here are the actual data transmission, PUSCH. I will not go in much details here, we are running out of time, but basically there is a whole formulas to define which sequence should be used and which orthogonal codes and so on. I will talk a little bit more here. Basically what happens is that for the DMRS, the modulation reference signal, a cell-specific base sequence is chosen, and then each one of those symbols, there are 3 symbol rows that are using the DMRS is sent. Each one of those symbols has a different cyclic shift, and then it has an orthogonal code applied to it. So basically we have then here the 12, length 12, that is the base sequence of length 12, shifted and with an orthogonal code applied to it. So what happens is that it is less prone to interference, and it allows the E and B then to synchronize and to adjust, equalize the receiver so it can extract then the information on the gray part where the data is. And for format 2A and 2B, that you remember, it's not is used for channel status information. It has less DMRSs, but also uses cyclic shift. The physical uplink control channel, basically for format 1A, 1A and 1B, it sends one symbol which is multiplied by the base sequence, and then a cyclic shift is applied. Well, the PUCCH delta shift, it's also published and informed through the RRC connection and RRC message to the UE. And basically it can be 1, 2, or 3. 1 corresponds a cyclic shift of 12, of 6, or of 4, and this basically is established by the cell range. Okay, so by establishing this by the cell range that is limited to 5 kilometers in reality, we know then which of these delta shifts the cell should send. Then we have the code index that is also informed, and is 0, 1, or 2, and it's informed for each UE, and that will help it to increase the orthogonality. So based on the delta shift, the total cyclic shift, the orthogonal codes, this is the number of orthogonal codes that are obtained. So in one channel, between 12 and 36 UEs can share the same channel, and for those distances. So if you have a very small cell, 1.7 kilometers, you can have up to 36 UEs sharing. If you have a large cell, you can have only 12. So what you need to do, you need to increase the number of PUCCH channels. And here I am showing the PUCCH configuration and the way the encoding is done, the orthogonalization is done, so the information can be sent differently for each UE. Format 2 sends the channel state information that is made of channel quality indicator, precoding matrix indicator, precoding type indicator, and rand indication. And this has from 20 to 22 bits because there are additional 2 bits that are the ACNAC. But the ACNAC is not really sent on the data part of the PUCCH, but it will modulate the DMRS. So the 20 CSI bits are clumped by a sequence based on PCI and UECR NTI, QPSK coded, resulting in 10 symbols. The 10 symbols are converting to serial parallel, and they go on the 2 slots, and this is easier to show here in the graph. and the 10 symbols are here. This is the scrambling part. Those are the 10 symbols. There are cyclic shift for each of the symbol rows, and then this forms the channel. Format tree is similar, has phase shift, has more orthogonal code, has cyclic shifts, and so on. I will not go in much detail here. Then we have the physical uplink channel, PUSCH. Well, this channel is really a conjunction of many different channels. So we have the CCCH, the DCCH, the DTCH. All of them form the uplink SCH, and all of this is sent on the PUSCH. Remember, we have the RACH and the PRACH, and we have the PUCCH and the SRS. Okay. PUSCH carries, that's very important. Although the PUSCH in principle should carry traffic, it really carries control also, because up to release 10, you could not send the control channels and the data channel at the same time. So you have to choose or one or the other. After release 10, you can send both together. And the reason for it was that the principle that the SC-FDMA will provide a better results, and in the end, the 3GPP really gave up on it and allowed you to spread the information more, because redundancy became, not redundancy, spreading the information gave more robust signals and so on. Although it still uses SC-FDMA, but it's not really giving us much benefit. PUCH uses KPSK, 16 QAM and 64 QAM, and it has the modulation is indicated in the uplink DCI formats. So that's where the PUSCH is sent here. Basically, a transport block, and the transport block in the uplink is very similar to the transport block in the downlink. So this transport block receives a 24-bit CRC. And similarly to the downlink, it is segmented in code blocks due to the turbo code limit of 644 bits, I believe. And then a CRC is added by block. Then we do turbo coding at 1/3 for each block. We do rate matching, and we do code block concatenation. Because this channel carries also the control information, so we take the CQI, PMI, the rank indication, and the ARC, and we apply the FAC, and all of this is multiplexes and send to the channel and send and transmitted. The PUSCH also has the MRS, because it can be sent in a different part of the band, and basically this DMRS, the sequence depends on the PCI and on a cell-specific offset that is used really only for multi-user MIMO. And there are some limitations of using multi-user MIMO. The size, the number of transmit blocks must be the same. So that's one of the limitations of multi-user MIMO. Release 10 try to resolve this and allows transmission over up to 4 antenna ports by adding orthogonal cover code to provide an additional dimension of differentiation. Okay, so this is the release 8 and 9, and here you have the extra orthogonal code for release 10. Let's speak a little bit about sounding reference signals. What happens is that in the uplink, the transmission is a set of contiguous resource blocks. And they need to be contiguous because of the SC OFDMA. And but they can be anywhere in they can be allocated anywhere along the frame. So if we go to the here, this can be allocated to this side or to this side and so on. So this is one UE transmitting, this is another UE transmitting, this is another UE transmitting, and those UEs are transmitting, have to transmit a contiguous number of resource blocks. Basically what happens then is that there must be an optimal location. That was the 3GPP idea, that there must be an optimal location in each UE to transmit optimal location in the frame to transmit a certain the information. So if one part of the frame is having fading, well, let's transmit in the part, let's allocate to that UE the part that doesn't have the fading. And to gather this information, then the sounding reference signal was created. The sounding reference signal is signaled also in the SIP2, where its location is, so the NB knows where to receive it, or the UE knows where to send it. And the way it should send, basically it eats part of the last symbol in the subframe, but it's not sent very, very frequently. So, and this information then is used by the ENB to help it to schedule better the resource allocation for the UE. Okay, let's have a break for questions.
Yes, Leonard. Like I said, we have a lot of different questions here. Let me take one here from the loop because we are running behind schedule again. Which of the resource scheduler solutions do you recommend?
Which of the resource scheduling solutions? Well, we will address the reuse in the next topic, so I would defer this to the next topic. Yeah, we are really running really late. I will have to probably go to the next topic, and I will speak, will give you, actually the next topic is the reuse, and we will resource assignment planning and ICIC. So let's speak about reuse in LTE. Basically what happens is that reusing cellular generally we need a certain SNR. We have an RF signal coming from one base station, an RF signal coming from the other base station, and here we don't have enough SNR, so cell A only provides service here and cell B only provides service here. And this is then the area in the middle. We'll have to use other cells with other resources and so on. The question for LTE was, well, what is the ideal resource reuse to use? And 3GPP said, well, let's use reuse of 1. Well, reuse of 1 is counterintuitive, but you will see that we did some analysis here to show it. Basically what happens is that reuse of 1 will also provide a lot of interference, but this interference can be overcome by increasing the strength of the signal through repetition. So basically what 3GPP did in LTE is to design everything for a reuse of 1, so the FEC can detect and correct signal errors, and additional strength is added by retransmitting the signal several times. And we can have repetitions from 8.5 times to 1.1. For central control signals, we repeated 25 times, as we already saw in the downlink. So the question is, which reuse will result in the highest throughput? So what we did, we created a set of cells on a flat area and so on, with a cell radius of 850 meters, 19 cells, tower height of 30 meters, flat terrain, no morphology, 30 dB per decade slope. Okay, and then we did reuse of 1, reuse of 3, reuse of 9, reuse of 12, and reuse of 21. Basically, when we say reuse here, we are reusing the resource blocks. We have only one wideband channel, and we are reusing the frequency, the resource blocks, and analyzing the interference. We came up very interesting results. So for reuse of 1, the SNR is generally negative. The bulk of the SNR is negative. So there is more noise than signal. Here it's a little bit positive, but it goes until 5. The best case is 10 dB. While reuse of 3, the bulk is positive, and it goes all the way to reuse of 20. And the reuse of 21, the bulk really is on the SNRs of 18 dB, 20 dBs. So, well, the first conclusion is let's go to reuse of 21. But what happens in reality is that we also divide the capacity of the system by 21. So we did then another analysis, now multiplying by the modulation scheme that can be used with the different SNRs, and this is reuse of 1, that basically confirmed what we had before, and so on. And then we calculated now the cumulative number. And basically the spectral efficiency for reuse of 1, it flattened here, but surprisingly it gave a slightly better, I would say, nearly the same result as reuse of 3. Reuse of 3 has an advantage that the instantaneous throughput is higher because it's using more modulations, higher modulation schemes. But reuse of 1, the instantaneous throughput is smaller, but it accommodates better, and we can reuse all the resources. So I would say that it's up to the user to decide between reuse of 1 and reuse of 3. My personal trend will be to go with reuse of 3 because I will have a faster instantaneous throughput. And here we did an analysis with a flat traffic distribution. If we have a concentration of traffic in one area, this will change. We have many other studies. I really We don't have time here to show all of them. We did with concentrated traffic, different azimuth, different orientations, and so on, because all of these help us to better design our customers' network. So here is the MCS occurrence per area. You can see here reuse 1 and here reuse 3. So the MCS used mainly in reuse 1 goes up to 10, while reuse 3 starts in 6 and goes all the way to 26. So basically here you never will have 64 QAM in reuse 1, or nearly never. Here we use the spectral efficiency, and again then the cumulative throughput, and you can see here that those two are very close in the end. So reuse 1 gave the highest throughput, 19% above reuse 3, but it has some deficiencies. And here we show some tables and so on. We really went very deep in this analysis, and here we analyzed, what is the SNR required for each type of for each SNR. What is the reuse required for different slopes and so on. There's also a study that we did. And then we're going now to address the question resource assignment planning. So basically a resource scheduler can be of 3 types: start, stop, start, and random. Start, stop basically can be used to assign blocks of RBGs to implement reuse of 3, suppose, or reuse of 9. So it assigns blocks of RBGs, and based on this, then we can implement the reuse. The start solution is very interesting because it doesn't have a stop. So if you give starts using, suppose, a reuse of 3, it will reuse the 3, but then when the traffic is overwhelming, is reaching the capacity, it will start having areas where the reuse of 1 is being used. So it should give a little better performance than the start-stop. And the random really is to avoid planning. So when the operator or the designer doesn't want to do planning, we don't recommend it. It will certainly give a worse performance than the other options, although it will be a kind of reuse of 1. So I probably will stick with the question and say that I will use the start solution. Design it for start-stop and then implement the start. Just some words about small cells and heterogeneous networks. This is something that we are getting a lot of questions about, and you need to design and plan those networks because the traffic is growing, and we need to introduce small cells and heterogeneous network. So when you optimize a network, you have to consider small cells and head nets, in head nets. So first question is, what is a small cell? Well, each person you ask, they will give you a different answer. For us, a small cell is a microcell or a metrocell that is using distributed antenna systems, a picocell, a repeater cell, a relay cell. The difference between repeater and relay is that the repeater is transparent to the ENB, while a relay sends its information using the ENB as a backhaul. A cloud run, a femtocell, a home ENB, or a Wi-Fi hotspot, all of those are small cells and have to be designed inside the network. optimize the network. Another new concept that is coming is the concept of backhaul and fronthaul. All the networks today, they are limited. One of the limitations, many times, we are called to check a performance of a network, people are complaining, and the issue is not the wireless, it's the backhaul. But now we have a new concept that is the fronthaul. There is a trend in the industry to concentrate the BBUs, the baseband units, in one place that we call hoteling, and to connect those BBUs to the RRUs, remote heads, radio heads units, using what we call a fronthaul. So we still need a backhaul, of course, but now we have another connection that is the fronthaul, and this is becoming more and more popular. So all of this creates what we call heterogeneous networks that are drawn here. Basically, we have here an UTRAN core, UMTS, that is connected to the PSTN. We have the evolved packet core, that is the LTE core, that is connected to the internet and connected through the IMS to the PSTN, but it's also connected to IP clouds. Those IP clouds interconnect ENBs. They interconnect picocells, relays, repeaters, metrocells, and microcells. And here we have an example of cloud computing, cloud runs, CRANs, that connect to a cloud computing center that can be together with the, or close to the cloud, to the RAN, or it can be centralized in the core. So we have the CRAN head, and then we have the computing, cloud computing center, and this really is what we call the fronthaul. And finally, we have femtocells that also connect to the cloud. A new concept that is also coming forward is the design of home ENBs that do not connect wirelessly, but they connect to the internet, and then they arrive at the core. So this is becoming more and more popular, and we have also Wi-Fi hotspots that also are carrying some of the traffic as offloading the wireless networks and so on. So one way of optimizing wireless network is to consider the design of heterogeneous networks using backhaul and fronthaul. Intercell interference coordination, there is a lot of buzz in the market about it, and people are proposing and doing, promising a lot. Well, LTE was designed with the use of 1. So for light loads, there is ways to, ICIC can avoid conflicts between adjacent cells. But this can also be done, with a start-stop scheduling, or a start scheduling will give the same result. So trying to, ICIC has not a major role here. It's questionable how much it can help, but the idea is to avoid resource planning and let this system try to adjust itself. The problem is, we will illustrate in the end, is that when you don't have an idea of what is happening or what is being done, conflict is unavoidable, and then you don't know how to fix it. So ICIC has to be taken with certain caution. It can be applied in frequency and time domains. So some RBGs are prioritized, subframes are prioritized, and basically it's a real-time allocation of resources. It is important when you use micro, pico, and head nets under a macro umbrella. It uses the X2 interface, and basically the 3GPP provide some help to ICIC, some reports. One is the uplink interference overload indication. Another one is uplink high interference indication, relative narrow band transmit power, almost blank subframe information, ABS, and invoke information. So basically, it doesn't, the 3GPP didn't solve the issue. It says, okay, you guys, vendors, operators, do whatever you want. I am giving you just some extra information that you can use. Now it came with the advanced, enhanced ICIC, because the original was very, very limited, and basically it added the blanking of subframes in the time domain, because when you are using microcell or small cells inside a macro cell, interference is unavoidable. So the only way of solving this is for the macro cell to exclude some subframes, and then those subframes are used by the small cells, and that's what we call almost blank subframes. Another use of ICIC is for intercell load balancing, so trying to do semi-static allocations, trying to divide the traffic between different cells. Adaptive partitioning, again using ABS, so trying to divide the traffic between macro and micro cells. And basically this is a repeat of what I already said. Also, ABS is performed in time domain, but it's also possible to do this similar thing in frequency domain, mainly when carrier aggregation is used. So basically ICIC helps with cell edge throughput, but only at low, moderate, and moderate traffic load. It does not increase cell capacity. Its gains are reduced with high load. And enhanced ICIC is basically for head nets. One important consideration is that the 3GPP is still working on a solution that will be self-adjusting. These attempts are in very preliminary stages and are far away from replacing traditional resource planning. The risk with ICIC deployment is depicted here by this picture. So it may work, but if it doesn't work, it will be very hard to fix. So summarizing, dimensioning and planning LTE network is not a trivial task. There are tens of important parameters that have been properly dimensioned. We probably listed here 40% of the parameters. Of course, the other 60% are not so important, or they are important, but they are easier timers and things like this. Finally, we can, of course, optimize a lot by the network performance by fine-tuning those parameters. knowledge of traffic characteristic is very, very important, and an advanced methodology and tool should be used to achieve the desired results. Okay, before we go into our new products, questions?
Leonard, we have a long list of questions here. In the interest of time, I think that maybe we should just proceed, and we will get the answers to the questions to the respective parties via email.
Okay, Roy, thank you. I apologize, people, but as you can see, the topics are very extensive. We generally take days to do this topic, so I had to compress it very, very much, simplify it as much as I could. We are proud to announce our new product, CelSpectrum Cell Designer. CelSpectrum, it will be part of the next webinar. Basically, we do 3D scanning of the broadband channel, and we are able to represent things like multipath, like RF channel response in 3D, fading, and traffic usage, and so on. We can also analyze the correlation between antenna, the potential for MIMO, and we can then transform drive tests into continuous predictions. We have a CelSpectrum analyzer that the difference with this spectrum analyzer is that it captures the spectrum and it stores the spectrum, so it allows you to look at the spectrum, not just a picture, but look to the whole spectrum at the moment you want in the lab and so on. So you can send some people just to collect it, and then the analysis can be done in the office. And Cell Designer is a new generation of planning tools, a collaborative work with operators. And your input is very valuable. We are developing this tool at this moment. It should be available by the end of the year, beginning of next year. And it's a new generation of planning and optimization tools, something not seen or not existent in the market today. It's really an unbelievable graphical interface and a very, very powerful tool that does automatic resource planning, cell planning, and does performance predictions, fully integrated with Google Earth, not just Google Maps, field measurements, provides a network master plan for SON and ICIC, and integration of KPIs. And thus, of course, integrates the backhaul planning inside the tool, not as a separate thing, but something that is embedded. And with this, we conclude today's webinar. I really appreciate your participation, and we are very, very pleased of having you, and I invite you for our next webinar. Roy?
Yes, Leonard, thank you very much for that very good presentation. I'd like to thank all the attendees for attending the webinar. Please note that the recorded session of this webinar, including the slide deck and the questions asked during the session, will be available on our website later in the week, perhaps by latest tomorrow. Also, as Leonard mentioned, the next webinar will be on October 1st. The registration is available on our website for that. Please go ahead and register. Our seating is limited. Thank you very much for attending, and we hope to see you on our future webinars. Thank you.